Okay. It's being very slow for some reason. Oh, nice. Thank you, Shashwat. So Shashwat has made a very nice poll on Telegram. That's one of the things I really like about Telegram, is the ability to add polls. Of course, that is polls spelled with P-O-L-L-S, not P-O-L-E-S. I don't know if anybody will get the joke. But so we have some good news. We have some fantastic news. Welcome, everybody. Donald Trump is fired. So that's fantastic news from my perspective. And I don't bring politics into the classroom, but in this case, I make an exception because he is a horrible, horrible person. And I think we have seen enough of his face. So even what we have seen will go down in history. So I'm not a proponent of censorship, but somehow I think that all of us would like to collectively forget the last 4 years ever happened. And of course, even though technically, I mean, he is only the president of one country, the United States. The way the world works, what happens in the United States affects everybody. And it's very important that the United States should have somebody who is at least at the very minimum a decent human being. And so last week was a very stressful week for me. I was following the election the whole time, and so I'm very happy. Okay, all right. Now, of course, that doesn't mean that all the problems in the world will be solved, but at least we will have a better shot at trying to solve them, because there is somebody who will try to solve problems rather than create them. Of course, there might be some of you, or perhaps many of you, who actually like Donald Trump, and for you, I mean, my condolences. Maybe he will come back in 2024. Who knows? So life goes on. All right. So good morning, everybody. Now, last week we were talking about harmonic oscillator, and we as people were asking, what is in homework 4? Well, whenever I say something like this, show, that's a homework problem for you. Okay. So what we found is that we can write down these operators, A and A dagger, and these are creation and annihilation operators. So the Hamiltonian can be written as something called a number operator. Now the question is, what is the meaning of creation and annihilation? What are they creating? What are they annihilating, right? So what is happening? Okay, so let's try to understand the physics of the simple harmonic oscillator, right? So it's actually fairly straightforward to understand in terms of this phase space picture. So what is happening is, right, that first of all we have these eigenstates which are eigenstates of the number operator. Okay, this is one thing, right? Then the second thing is that if you take the norm of this, if you take the annihilation operator acting on n, what we find is that this is equal to root n ket n minus 1, right? So this is the second thing. Now from this, or maybe better to call it 2a, then we can take the norm of this state, right? So if you take the norm of this state, what is that equal to? That gives us n a dagger a n, right? I'm just taking this guy and taking the bra of this vector and contracting it, taking the inner product with itself, right? So if I take the bra, what happens? I get bra n times a Hermitian conjugate on the left side, and on the right side, what I will get is n minus 1, n minus 1, right? And now both of these are both greater than or equal to 0 by the fact that these are both norms, right? So this implies that n is also greater than or equal to 0. Okay. Now then one can ask, can you place any further restrictions on n? So can n be any real number, right? And so the answer to that is no, right? So what is the smallest possible value of n, right? So what happens is, if you start, let's say you start with some n, or some, no, not capital N, because that's number operator. Start with some n prime, okay? Let's say greater than 1, okay? Then what happens with if you act on this state corresponding to n prime, where n prime is equal to m plus epsilon, where m is an integer, okay, and epsilon is a real number. Okay, I'll write epsilon like this. Epsilon is a real number between 0 and 1. Okay, so if you take a and act on n prime, what will you get? You will get a acting on m plus epsilon, and that will give you root of m plus epsilon times root of m plus epsilon minus 1. Okay, so now if epsilon is not 0, okay, so if epsilon is not 0, then what will happen, right? If you keep acting on this m plus epsilon, you will get m plus epsilon minus 1, right? m plus epsilon minus 2. You keep acting on with a each time, and until you will get reach m plus epsilon minus m, right? After acting on this guy with the operator a m times, you will reach this, which is what? Which can be written as this thing, epsilon. Okay. But now the thing is that epsilon is it lies between 0 and 1, right? And if I ask what is the number operator, right? The number operator acting on epsilon, right? Number operator is this guy. It should give me this epsilon. Okay. But again, if you okay, so now the thing is that if I now act on this with a, what do I get? Right? If I act on this with a, is my screen not updating again for some reason? Okay. What will I get? Will I get epsilon minus 1? Right? And no, right? Because epsilon minus 1 will be less than 0. Right? And as shown previously, for n has to be greater than or equal to 0, right? For eigenstates of the number operator. So what is the possibility that we are left with? The possibility that we are left with is that so if this action of A has to be well defined, then what are we left with? Epsilon must be equal to 0, which implies that m must be equal to a positive integer only. So what happens is that A acts on n, you get n minus 1, n minus 2, until you reach, let's say, 2, then 1, and then finally the state 0. Okay. Now, once you reach the state which is 0, then you cannot go to anything less than 0, right? Because again, that would violate the restriction on n being greater than or equal to 0. So therefore, A dagger acting on 0 should be equal to 0, right? So this is something that is a requirement, right? I mean, I think maybe one can actually prove this. I'm not, not sure how to do that. So I'll just leave it as a requirement for the time. Okay, but it's a reasonable requirement, right? So this is the ground state of the system. Right? And what is the action of the Hamiltonian operator on this state? The action of the number operator will give us 0, right? Because in the number operator, the first term is A acting on get 0 gives us just 0, right? And so we are left with 1/2 h bar omega. And what is this h bar omega? This is the ground state energy, right? So the lowest energy ground state has non-zero energy, right? So if we ask what is the energy of, so I'll write it like this, E naught by 2. Okay, so this is the ground state. Now what is the next? What is the next excited state? The next excited state is, or the first excited state, how do we obtain it? Well, we act on this state with a dagger. Okay, when you act on this state with a dagger, you get root of, you get the first state, first excited state, right? Because this is the action of the a dagger on the number eigenstates. Now, and what is the Hamiltonian of on one? Well, so you have the number operator acting on one will just give you one. So you will get 1 plus half. So you will get 3 halves h bar omega times get 1. So this is the next excited state, right? So the next excited state is get 1, and the energy of this excited state is 3 E naught by 2. And what is the gap between these? The gap is h bar omega naught. Right? So you can see that the energy difference between is h bar omega. The energy difference between any two consecutive energy eigenstates of the Hamiltonian is h bar omega. And so what you find is that the energy spacing is linear, right? No matter how high you go to, how high your energies are, you will always get a linear spacing, right? So you'll get you will get a linear spacing, constant spacing, in fact, constant spacing. And what is the spacing? It is h bar omega between each consecutive energy eigenstate. So, right. Okay. And so what happens if you have a particle which is in such a potential of a harmonic oscillator? Okay. Well, it will absorb and emit quanta of energy, and those quanta of energy will always have energy which is given by this h bar omega naught, which is a constant. Okay. Now, so are there any questions about this so far? Is this clear to everybody? Are there any questions? Okay. All right. Now we can actually solve. So we have this equation, right? Now remember that so far we have not given the exact form of these states, right? As so for these states, we should have some expression as functions of the position, for example, right? So for the single particle in a box, uh, the uh, the states look like sine function, sine or cosine, depending on your on the coordinates of the box. So the question is, what is the similar expression for these states? So in other words, now the question becomes, what is this, right? So if I take my position eigenstates, and if I then my wave function, right, what I call psi of x, will be the projection of my state on the position eigenstate, right? And so this is true for an arbitrary state, right? So if you have the nth eigenstate, I can write this as psi of n x, right? So this is the same thing that we do, for example, in infinite potential well. What happens, right? We remember that this psi of nx, right, which you write as root 2 by L, then sine of n pi x over L, right? For x living in this range, 0, L. If you move the box, then you will change the form of this function. So for this is what? This is actually, what is the full state? The full state is actually this expression, right? This is the full state, right? This is the nth eigenstate, right? And these are the components of that eigenstate. So if I ask what is psi of nx, psi of nx is actually the projection of this n onto the x eigenstate, right? Again, just, I mean, we tend to forget these things. So let me again remind you, you have some arbitrary state, let's say psi, and psi is written as some superposition in terms of some eigenstates, phi I, let's say. Then what is C of I? C of I is equal to this quantity, right? It is a projection of the state psi onto phi, right? So here what do we have? We have that the state psi, right, is written like this. These are the basis states, like the phi I, these are the basis states. Only now our index is a continuous number instead of a discrete number. And this is actually an abuse of notation. Instead of writing psi of x, if you want to do the same thing as you have done here, then what one technically should do is write something like C of x or C of x, right? X as a subscript. But because historically it has been written as psi of x, we write it as, in this way. And I think this causes a bit of confusion. But the important thing to remember is that this psi of x, what is this? This is actually the coefficient of the state. It is the component, it is the coefficient of the x eigenvector. And so again, the same way as this C of I is equal to this projection, the same way C of x is equal to x of psi. Right? Just to remind you all, in case this might have forgotten this. So coming back to our harmonic oscillator, we have our zero state, and we have to figure out what are these coefficients. When I write this zero state in the x representation, what is psi naught of x? Okay. So to do that, so this is sidebar. Okay. So to do that, now we have to use this equation. All right. So we have to solve this equation. And how does that work? So we need our expression for the annihilation operator, which is A naught. And what is that expression? Right. So we need this expression. Okay. So this is my annihilation operator, right? And I'm asking that my zero state satisfies this equation, right? Okay. Now in this expression, so we can now solve this this equation, right? So let us take the operator P to be our usual in the position representation. We are working in the position representation. So in the position representation, the operator X will just become the number X, and the operator P will become dH by d by dx, right? So this expression will then become, if you put this minus here and get a plus h bar, you will get a root of h bar over 2m omega d by dx for the momentum part, right? There's a h bar here and there's a h bar here in the denominator, so square root, so you'll get a square root of h bar on the numerator, and then plus m omega by 2h bar x hat acting on 0 is equal to 0. Okay. All right. So now what we can do is we can write the state 0 as in this way, right? Now, and then we substitute this expression here. So the result is that this is our equation, right? And since this is a vector which is identically 0, so that means that this should be equal to 0, right? And so when you have this x operator acting on x will just give you the component x, number x. So we are left with this equation, and this equation is just a ordinary differential equation. Okay, and we can take out some factors which are common. So let me take out this factor of m omega 2 h bar. So I get x plus, here I'll get h bar by m omega d by dx sin of x equals 0. Okay. So now I have to solve, if I rearrange the terms a little bit, what do I get? D by dx of psi naught x is equal to minus m omega by h bar x. Okay, this is my differential equation for psi naught. Oh, and psi naught x. Okay. Any questions? Questions? I'm having some trouble with getting the YouTube version to load. So if there are any questions from the people who are watching on YouTube, I don't know, I can't see them. Maybe they can ask on WhatsApp. Okay. All right. So this is our equation. Now we can solve this. We can integrate this. Anybody wants to volunteer for how to do this integral?
Sir, we can take psi naught x uh, below the d psi naught x differential, yes, sir. And equal to minus m omega h cross integral x dx. Yes, sir.
Right, and good.
Yeah.
Then we integrate both of these. So on the right,
ln,
what I get? Huh?
ln psi naught x equal to minus m
Yeah,
omega
right.
h cross
Right,
x
right,
square
right.
by 2.
Okay, so this is, now we can integrate. This is log of psi naught x, and what is this? This is minus m omega by h bar x 1/2 x squared. Okay, and again, as usual, we have to be careful with our domain of integration. So let's say we go from x1 to x2, d sin of x by sin naught is equal to integral of this x1 to x2 minus m omega by h bar x dx. Okay, so on the left we get log of psi naught x2 by psi naught x1. On the right we get minus m omega by h bar square, x2 squared minus x1 squared. Okay, if we set x1 to be 0, let's say, then and we say x2 is equal to just x, then we get psi naught x is equal to psi naught at 0 times exponential minus m omega by h bar x squared.
Sir, upon 2 h cut. No.
Sorry.
Upon 2 h cut.
Sorry. Right. 1 second. H bar. It's pronounced H bar. Okay. Okay. And then this will just be the normalization constant. So the ground state solution of the harmonic oscillator looks like, if you make a plot of this solution, so this is the potential, and then the solution is this is the Gaussian. This is the potential, and this is the Gaussian. Okay. Of course, my Gaussian is tilted a little bit, maybe a little bit better. Okay. By the way, I wanted to mention one thing to you all, that you know how many of us only have mobile phones, and we are always wondering how to make plots and all. So I think I hope everybody knows that you can find like many nice apps in which you can make all of these plots. One very nice app that I know of is called GeoGebra. So this is a beautiful app. It's free, and you can do all kinds of crazy things with it. Okay, so for example, I'm just this is a ready-made file. Okay, this is one of their sample files. So you can see that one can change the amplitude, one can change. One can even have interactive plots like this, and right, and one can do more interesting things. For example, you can ask what happens, and then you can zoom in and zoom out. Right, it's a beautiful app. So you can define two functions. You're defining one function, f of x here, which is this polynomial in the green curve, and g of x is the exponential curve, a to the power of x. And you want to find the roots of this equation. What is the equation? That this the equation is that this polynomial is equal to this a by x, right? So how do you do that? You just use this function intersect, okay? And if you say intersect, it will automatically find the roots for you, and it will tell you where the intersection are, where the intersection lies. So one of them is over here, another one is over here, and then there's a third point also, which is not mentioned. But okay, so this is a very beautiful app. I strongly recommend that you all use an app of this kind. All right. So this is the ground state of the harmonic oscillator. Okay. Then what the question now is, what is the normalization calculate? Okay. And again, wherever I say this, show or calculate, that means it automatically becomes a homework problem for you. So it's a very straightforward problem. It's an integral of a Gaussian, and if you don't know how to do the integral of a Gaussian, look it up. That's a very simple. It's a simple calculation and something that you should know how to do. Okay. Okay. So now the next thing is, what about the higher states? What about n, where n is 1, 2, and 3, and so on? Okay. How do we get those states? So now we can do that in the same way by noting the fact that if I take my A dagger and act on the ground state, what I will get is I will get 1. Okay. And so now I know what this thing is. This is a Gaussian, right? So if I take if I want to find what is psi of 1, I want to find this guy, psi of 1x, right? Which is the x component of the 1 state. So then this is equal to x of 1, psi of 1x is equal to x A dagger 0. Okay. And once again, what is 0? 0 we have already figured out. The 0 state is this guy, where what is psi naught? Psi naught is some normalization times this Gaussian exponential. So what do I have to do? I have to substitute for the 0 state, I have to write down psi naught. Now I have to use a different x. I have to use x prime because x is already used over here, right? And then what is A dagger? A dagger, if you remember, if you write down what is A dagger is just going to be the complex conjugate of A, right? So the complex conjugate of A, what will happen? I will just get a minus I over here. So if I put a minus I, that will change the sign of the this d by dx. So if I put that in here, what will happen? I will get A dagger is equal to this, right? And so then I take this A dagger and I act on psi naught. And when I act on psi naught, x acting on psi naught will just give me x times psi naught, x times an exponential. Then I have d by dx times that exponential. And so this expression can be written as in this form. So when you insert this and you work it out, what you find is that psi 1x can be written as some normalization C1 times again this exponent of minus m omega by 2 h bar x squared times h1x. And what is h1x? H1x is going to be a polynomial. So it will be a polynomial in x, and it will be something like x and then d by dx. Yeah, for this will just be proportional to x. Then h2x will have. So then, if you want to find out what is psi of 2x, right? Psi of 2x. Psi of 2x is this. And what is this 2? 2 is equal to a dagger 2, but now you have to divide by root 2, because if you remember, a dagger acting on ket of 2 is equal to root 2 times 2. So you have to divide by root 2 here.
Sir, I think it's a dagger of 1.
Thank you. A dagger of 1, right? A dagger of 1. So you have 1 which you found here. You substitute this expression and you get psi of 2x is equal to, again, the same procedure, psi 1 x prime dx prime. Okay, and then this will give you psi 2x. So so in general, what you find is that psi of nx can be written as some normalization times exponent m omega by 2 h bar x squared times h and x, where h and x are called the Hermite polynomials. Okay. So now I'm going to give you some problems for homework number 5. Or for the MSc people, we can make it part of homework number 4, since you don't seem to have enough homework problems for homework number 4. So what are the problems? Let's see. Number 1. Using the above procedure, determine the first 3 Hermite polynomials, h1x, 2x, and 3x. Okay, and calculate the normalization coefficients for the state C1, C2, and C3. And number 3, show that these states are orthogonal to each other. So yeah, okay. Yeah, so show that this is 0, And so for the first three states, show that these inner products are explicitly zero. So in general, what you have is, right? In general, if you have this MNN, this is equal to delta MN, right? This is a set of orthogonal eigenstates. It's a complete set of basis vectors for your Hilbert space. All right. So this is now one of the things I started off talking about, but then I got a little sidetracked, I guess, is what happens, what is the effect of these operators? So the effect of these operators, so first of all, you have the ground state. So the ground state corresponds to the smallest possible trajectory. And you remember I told you that the area of this enclosed by this trajectory is going to be a minimum. Then when you act on this state with a dagger, what you will do is you are increasing the energy. So that corresponds to a jump from this trajectory to the second line, right? Then again, if you act with a dagger, you jump to the next highest trajectory. And each time, what happens is that your energy changes by a discrete amount, finite amount. So in between these regions, over here, you have energy states which cannot be occupied. Okay, but this is not a precise characterization of the quantum state. Okay, what is the reason for this? Because these are classical trajectories, right? Each point of this trajectory corresponds to a exact value of x and p, right? But x and p cannot be simultaneously measured for a quantum state. So for a quantum state, what you have is that delta x and delta p will be, there's a minimum value. So instead of a single point, what you instead have is you have something like a fuzzy ball, a ball-shaped region that moves in your phase space. This will bring us to the topic of coherent states, which are one of the most important tools in quantum mechanics. And so we will talk about these states. With the MSc students, I will talk about it in your next class. So the next class onwards will be MSc only. Of course, anybody is free to attend my classes. So for BTech students who are interested in continuing their education of quantum mechanics, they are welcome to attend my future classes. So yeah, so for MSc people, homework 4, please remember, these are the additional problems that you have to solve. Okay. Any questions?
So, pardon the noise in the background. There is something going on. My doubt was initially any state that we consider when we phase shift it, we don't see a physical change in the properties of the system, right? But we don't like. Is the Schrodinger equation also the same way? If we shift the phase of the equation, it will still remain the same.
So here's the thing, right? I talked briefly about something called the Aronoff bomb effect earlier in the semester, if you remember.
Yes.
Right? And so in that, what happens is that you have an electron, and it can travel along two different paths.
Okay.
Now, when it goes along one path, it picks up a certain phase. When it goes along the other path, it doesn't change.
Yeah.
So when it reaches the end of these two paths, and you calculate the interference between the two paths,
Okay.
the phase plays a role,
Yeah.
right? So the absolute phase of a state does not make a difference.
Okay.
Okay, so if I have two different states, so let me send that on a new page. Okay, so if I have two states, let's say psi1 and psi2. Okay, and psi1 undergoes a phase by some angle theta1, and psi2 is shifted by some angle theta2. Okay, now if I calculate the norm of psi1, it is unchanged, right?
Yes, sir.
And the norm of psi2, these are both unchanged. Okay, so if I have anything which involves only psi1 or only psi2, then the global phase change will not make any difference. Okay,
Yes, sir.
but if I have psi1, psi2, any expression where you have the combination of psi1 and psi2,
We have a phase.
what will happen?
We e
Exactly.
bar theta to minus.
Here you will have right. This is interference.
Okay.
So as an example, let's say that you have some spin half state like this, okay? And it undergoes a global rotation, right? But under this global rotation, what will happen? The probability of 0 and the probability of 1, they will both be unchanged,
Yeah.
right? But if your if your phase shift is different, if 0 is shifted by some amount theta1 and 1 is shifted by some amount theta2, right?
Yes, sir.
And then you calculate what is the probability of getting 0. So this probability will be
the e bar minus I theta 1.
So there will be a one second. All right. So now let's say if you calculate the norm of psi, what will happen?
Oh yeah, this will
No.
still remain the same, I think.
No. So there will be a. So then let me write this as psi prime. E to the I theta 1 alpha 0, e to the I theta 2 beta 1. Okay.
Yeah.
Then I ask what is the overlap between these two states.
Yeah.
So
So
this overlap will be alpha squared times e to the I
theta 1.
theta 1 beta square e to the I theta 2.
Yeah.
Right?
Yes, sir.
So if there is a relative phase, so that because there is a relative change of relative phase between 0 and 1, that shows up in any experiment which involves this kind of an interference.
So we'll be able to measure it in some sense.
You'll be able to measure the relative phase. Yes.
Yeah. Okay.
You
We
can
won't
measure the
be
relative
getting
phase.
the absolute phase, so we can assume one
No,
of the.
absolute phase you cannot measure. Okay. You might find something called Berry phase. There is something called Berry phase. That's a very interesting phenomenon that happens. You can look it up if you are curious.
Yes, sir.
That is some.
I'll look at that. Yeah.
Okay.
Yes, sir.
All right. Any other questions?
Sir,
Yeah.
sir, in Stern-Gerlach experiment,
Mm.
the particles only go to top and bottom of the screen.
Mm-hmm.
Why doesn't they go in between?
Yukta, we've talked about this in great deal now.
Yeah.
The reason is because the spin is quantized, because the angular momentum is quantized, no? If it
Yes,
wasn't quantized,
but there will be some probability that it can go in between.
that's the whole point, right? There are no states in between. If there are no states, there is no probability also, right? The only angular momentum states are up and down. The up state will go in one direction, the down state will go to other direction. There is no state in between up and down. You have up and down, but there is no state in between.
But sir, initially the particle, all particles were unpolarized, right?
That's right.
So they were in the all direction.
Sure, but when you the measurement of the angular momentum along the z direction, you only have two possibilities, right? So what I would suggest to you is to, again, very good resource for this is there a Wikipedia page on Stern-Gerlach. It has a very nice video illustration of exactly what you're asking. So if you go and take a look at that, I played that in class also. So you go and look at that, and if you're not satisfied, you come back and ask me, okay?
Okay, sir. Thank you, sir.
Yeah, okay. Any other questions? Okay. All right. The homework number 4 submission is open for both BTech and MSc. Please submit for BTech people by this weekend, and for MSc people also by this weekend. And MSc, your quiz will be on Tuesday. Topics will be everything we have covered so far. Okay.